title of this talk is Integrability and Wilson Loops.
Okay, thanks for the organizers for giving me the opportunity to speak here. I will talk about some old results briefly, and then mainly concentrate on results from these last three papers. They're all contained in here, but some of them are already in brief versions in these older papers with these three guys. So in this conference, we're studying mainly the two-point function of non-supersymmetric operators in n equal 4 Young-Mills. And it's just a two-point function, but this is a hard problem. And it's just the beginning of calculating everything one might want to calculate. So one of the things that I've been calculating are Wilson loops. And those are obviously very interesting operators, but they're also much more complicated than local operators and then the two-point function. So it might be a big step to go from local operators to Wilson loops, and premature to hope to have the tools of calculating them. In this talk, I will present some results that relate Wilson loops to several integrable systems. So the main examples I have are the cusp anomalous dimension, which is related to the dimension of twist 2 operators, and then related to Clune scatter amplitudes, all that story. We've just heard about that, and we're going to hear about that later this afternoon, and I will not mention it at all. The examples I will mention is something to do with the way you calculate Wilson loops in ADS, and then it's the integrability of the ADS 5 crosses 5 sigma model. That's one place where integrability shows up. Another case where integrability shows up is when you consider a circular or a straight Wilson loop that is supersymmetric, and you consider an insertion of a local operator into it. Then you find open spin chains. So I will review that briefly, how the open spin chains come about. And then most of what I'm going to say is about a new family of supersymmetric Wilson loops, which we can get for an arbitrary shape curve on S3, where S3 is in space. And when you can consider an S2 subspace of that, you seem to find a relation to two-dimensional Young-Mills. So here's my transparencies on semi-classical strings. Wilson loops in ADS 5 crosses 5 are calculated by a semi-classical string at leading order. The string sigma model in ADS 5 crosses 5 is integrable, so you should be able to calculate all Wilson loops. Well, you should be, but in practice it's very hard. There is no algorithm for going from boundary data to calculating the minimal surface. And while in some cases, so integrability doesn't really help much, this word. In some cases, if you have a periodic motion, then there are such algorithms, and there are ways to take an ansatz, which is similar to spinning strings, and find explicit solutions. In other cases, like the polygons that you need to calculate gluon scattering amplitudes, if the duality is correct, it's not known how to do that. And just like that, staring at the equations of motion, nobody knows what to do. So this is still an open problem to try to see how integrability helps in this case, or for more general curves. But it seems quite hard as it stands. The next example has to do with open spin chains. And these are very similar to the spin chains everybody else has been talking about. So you consider a half BPS circular or straight Wilson loop, and that preserves quite a large symmetry group. In particular, it includes an SL2R group, a subgroup of PSU224. And then deformations of the circle or the line can be classified by representation of this group. In particular, near an insertion, if you take an insertion into the loop, near that insertion, one of the generators of SL2R will act like the dilatation operator. So we can assign a conformal dimension to local insertions into the Wilson loop. So this is the kind of thing I'm considering. These are all at the same point. These Z's and X's I have here, which would normally be a spin chain, and it's connected to this Wilson loop going to the past and from the past and to the future, and I can consider another one at some other point. So the main difference from the case of standard spin chains is that this insertion is in the adjoint of the gauge field. It's a product of matrices, and then if my Wilson loop is in the adjoint, then this entire system is in the adjoint. It's not a gauge invariant. It's not traced. And what I'm going to say now is just going to be a simple consequence of that. At tree level, I have to contract. If I have 3 insertions here into the circle and 3 insertions here, I have to contract them this way and just this way. There is no freedom of permutation or cyclicity. At one loop, there are these kinds of diagrams, which are very familiar to us from the work of Minahan and Zarembo. And they are exactly the same. So the interaction between 2 letters in this word is exactly the same as the standard spin chain, the PSU224 spin chain. The only new ingredients are interactions with the Wilson loop itself, which appear at the same order, but only the external letter can interact with the Wilson loop. The central one cannot. So just from looking at these diagrams and without even calculating them, you know that this system will be described by an open spin chain whose bulk is the same as the PSU224 spin chain, and then it has some boundary interactions which you have to calculate. We studied it in the case of the SU2, of some SU2 subsector, and we found an integrable open spin chain at one loop. Presumably, if you include all possible insertions, the boundary will break the symmetry to OSP 4 star 4, which is the symmetry of the circle, but this has not been done yet. So that is the other example of integrability in Wilson loops. And finally, I turn to my most recent work. First, I give another example, and that's finding supersymmetric Wilson loops and studying their properties. So I will review here a construction of Zarembo first. So I write here a general Wilson loop in n equals 4 gauge theory, which is supersymmetric. It's quite standard by now. You have here these scalars, the 6 scalars, and you include an extra coupling to them, where this coupling has to be of magnitude 1 for this object to be supersymmetric, but that is not enough. Because at every point along the loop, supersymmetry variation leads to an equation, and for the entire object to be globally supersymmetric, all these conditions have to commute with each other. So the way Kostya solved this is to take the scalar coupling, this guy, always proportional to this guy, as a matrix. So I take theta I to be a matrix M mu I, or x naught times this. So the entire thing, I replace a mu by a mu plus I m times phi, and I integrate that dx mu. So by this construction, you can see that if the curve is confined to a straight line, it will preserve half of the super Poincaré generators. It will couple to a single scalar. There will be just one tangent vector turned on. If it's in the plane, I'm going to get 2 conditions. It will be 1/4 BPS For an arbitrary curve in R3, it's going to be 1/8. And for a completely arbitrary curve in R4, it will be 1/16. So this is a way, by adjusting these scalar couplings, to get a supersymmetric loop for an arbitrarily shaped curve. As it turns out, all those loops have trivial expectation value, just 1. And this can be seen both in the gauge theory and in string theory, and there's the best argument comes from a topological version of n equals 4 gauge theory. So, well, I find it quite amazing, interesting, that there are these objects that are supersymmetric and their expectation value is 1. Such a large family of operators that whose value you know, there isn't much to calculate anymore because we know the answer. Also, this family of loop doesn't include the half BPS circular loop. This is a circle that couples only to one scalar, and by this construction, a circle in the plane will couple to 2 scalars. And this circle has a non-trivial vev. So our generalization was trying to find a similar construction that will lead to the half BPS circle. So how do we do that? Well, Zarembo replaced a mu by adding phi mu, where phi mu is this m times phi. I will take another object out of this. I will make another object out of a scalar. I will make a self-dual tensor, phi mu nu. And then I will replace a by a plus phi mu nu times x mu. So again, I get some vector. I can also write this in form notation. I replace a by phi times sigma I, where sigma I are 3 one-forms. So on S3, I can choose the right forms. On S3, I have 3 one-forms that are interesting, and I just take them. And well, here, the analog of writing it this way would be to take here exact differentials. Here, those are the left invariant one-forms on S3. And then you can also write it in terms of components. And these tensors are the 't Hooft eta symbol, and they are also the related to the generators of the Lorentz group in the anti-chiral spinor representation. So now it's just some algebra to show that with this definition, the Wilson loop is supersymmetric. And for a general Wilson loop on S3, for an arbitrary shaped curve, there will be 2 supercharges preserved. And these supercharges are going to be a combination of the super Poincaré generators Q and the superconformal ones S. So generically, it won't be that Q will not annihilate those Wilson loops, just a combination of Q and S. So that's the construction. And now you can look at some special examples. So one is to take a great circle on S3. A great circle will follow an integral curve of one of the vector fields dual to one of those one-forms. So it will couple only to one of the scalars. So that is the half BPS circle. But there are other integral curves for these one-forms. So if I choose this one form, it has a family of integral curves, and those are what we call the Hopf fibers. So if you write S3 in terms of the Hopf fibration, circles over an S2, if you take an arbitrary circle along one of these Hopf fibers, it will couple to the same scalar. So here there is a way of finding a family of circles. All of them, each of them is half BPS. They all couple to the same scalar. And you can check that the combined system will be 1/4 BPS. And actually, to the extent that we could calculate so far, it seems like there is the interaction between those circles is independent of their position. So they can be very, very close to each other, and they can be on orthogonal planes, and it looks like they don't talk to each other, or the interaction doesn't depend on the distance. So this is something like parallel lines in flat space. If you are on S2, you will preserve double the supersymmetry. So generically, you're going to have 1/8 of the supersymmetries. And then there are some examples on S2 which are 1/4 BPS. And if you take infinitesimal loops, near a point, these one forms become exact differentials, and you recover the construction of Kostya. So now we want to calculate them. And we don't have results for an arbitrary curve on S2, but we have something interesting to say when the loop is restricted to a large for S3, but we do have something to say about S2. In that case, the one forms can be written as the cross product of the vector and its tangent. So this is the form of the Wilson loop. And now I can consider the exchange of a gluon and the exchange of a scalar between 2 points on the Wilson loop. This gives me an effective propagator where I have the dot product of the two tangent vector and the dot product of these two factors. And now you use simple cross product identities to rewrite it in this way. This is quite interesting because you are in 4 dimensions where the propagator of a gauge field will, in configuration space, will have dimensions it will have mass dimension 2, but this combination has mass dimension 0. So it looks like a 2-dimensional gauge propagator. It actually is. So actually, if you take a circle, not an arbitrary shaped curve, the expression I had there is a constant. So all ladder diagrams are given by a 0-dimensional matrix model. But generically, this is a propagator on S2, and it's a propagator for 2-dimensional Young-Mills. Now that theory confines, as you know, but that doesn't match what we can calculate for those Wilson loop. And this is some ambiguity that was studied by some of the people here in the audience. Staudacher, collaborator in Bassetto and Griguolo. And in 2-dimensional Young-Mills, there is a perturbative prescription. If you ignore the instantons, well, there is a perturbative prescription that ignores the instantons and gives a different answer that is not confining. And our propagator seems like a propagator from that prescription. So we shouldn't get the full 2-dimensional Young-Mills result that confines. We should get another answer for the perturbative prescription of 2-dimensional Young-Mills that those people studied. And this is the result of their calculation. It's some function, an exponential, and a Laguerre polynomial of a combination of the coupling g squared times the product of the areas of the two pieces of the sphere that are separated by the curve, by the Wilson loop. And you can expand this at weak coupling, and you get another function of A1 cross S2 cross g squared. And you can do it at large coupling, and you get another expression. And now we can test it in specific examples. So one is a case where you take a latitude on S2. And in this case, we can do many different calculations, and in all of them, we get an expression that is just a function of g squared times sine squared theta. And indeed, the area of this region above is 1 minus cosine theta naught, and the area below is 1 plus cosine theta naught, and the product sine squared theta naught is exactly the product of A1 times A2. And this agrees with an explicit two-loop calculation in the gauge theory, a leading behavior from a string in ADS5 cross S5, and also an all-order 1 over n expansion in string theory, which you can get using a D3 brane. Another geometry we can study is a supersymmetric cusp. Two longitudes that meet at the cusp at the North Pole and the South Pole. And here we cannot do an all-order calculation, but we can calculate it at weak coupling and at strong coupling. And again, we get a result which is just a product of the two areas of these segments, 2 delta for the small one and 2 times 2 pi minus delta for the big one. So again, this result exactly agrees with two-dimensional Young-Mills to the extent that we could calculate it. So let me summarize. I presented some examples of the tools available to calculate Wilson loops and some possible connections to the integrability program. The first was the fact that the sigma model is integrable, allowing, in principle, to calculate Wilson loop, but in practice, I don't know how to do it. Local insertions into a supersymmetric Wilson loop into the circle give an open spin chain. My supersymmetric new family of supersymmetric Wilson loop for an arbitrary shaped curve on S3. They're a generalization of the idea of Zarembo, but they have non-trivial expectation values, so it's something that can be fun to calculate. One thing I did not have time to mention is for a general curve on S3, we find an equation on the string will be an ADS4 cross S2, and there is a holomorphic equation for those. I discussed the hop fibers, and when I said that on S2, the perturbative series seems to agree with two-dimensional Young-Mills, and all other tests we could do agreed with two-dimensional Young-Mills. And it's quite remarkable that if this really holds, that there is a subsector of n equals 4 gauge theory that is invariant under area-preserving diffeomorphisms. So it's a function of the area, not of angles, which is quite weird. That's it. Thanks.
I remember from our paper with Mike Douglas that for simple Wilson loop we had the Bessel function in the strong coupling phase, the downstairs, the formula downstairs.
Yes,
and the upstairs it was the elliptic, some elliptic integral. Is it the same story? You have weak coupling, all these wrappings of surface here? Or is something different?
I'm not completely sure. I have.
The result from Young-Mills, from your Young-Mills too?
The large n limit Lagrange polynomial not the best.
Ah,
Yes.
I see. This is for finite n.
This is for finite n.
And,
Yes.
And downstairs also?
This is for infinite n infinite lambda. This is the approximation to the Bessel function.
Then Bessel function
becomes exponent. Yeah, it has an imaginary argument. So normally you would have a J Bessel function. This is, in this case, it's an I Bessel function, but that's the limit of it, yes.
Any other questions? A very naive question about the Wilson line. So you don't include fermionic coupling?
I didn't. In principle, one could. You need to add parameters to couple to them. You have to.
So you have some graphs.
Yes.
Why don't those couple? The thing you wrote down doesn't look super. I believe it is, but I don't understand.
Well, it's the same way that phi 1 plus I phi 2 z is supersymmetric.
Okay. One quick question. Do you expect that the interactions cancel for the loops on S2?
No. Not in this, not in the Feynman gauge. Then it will not work.
Okay, let's take that out again.